Hello, my name is Ian Wilson, and today we'll be talking about control flow hijacking. So first, let's start with a review of processes and stacks. Peeking inside a process, we have a virtual address space on the right. An address space is a set of virtual memory addresses a process is effectively allowed to use. A virtual address space can be partitioned into four main sections. We have the text section, this is where your compiled code lives. The data section, this is where initialized global and static variables are located. The heap, which is the region of memory that grows upwards as your program allocates memory dynamically at runtime. And the stack, which is the region of memory that grows downwards and temporarily stores variables, function arguments, and return addresses. Kind of go do some review over stack basics. The stack just stores important information to execute a particular function, including function call arguments, temporary variables, and return addresses. Each time a function is called, it creates a stack frame, and data is placed on and retrieved from stack frames via registers. So on the right, we have a caller who has saved their return address as well as their saved base pointer onto the callee's stack frame, where the callee will then allocate its own local variables to some given stack memory that's past the caller's saved RBP. Some important registers to remember for stacks is the base pointer, which points to the base of the stack frame, the stack pointer, which points to the current top of the stack, and the instruction pointer, which is pointing to the currently executing instruction in the text section. So now we're going to be talking about stack smashing, starting with buffer overflows. So if you take a look at this program, can you spot the vulnerability? If you said the vulnerability was at line 10, then you'd be correct. So why exactly is line 10 vulnerable? Well, line 10 is vulnerable because in programming languages that are low level like C, there's no bounds checking being made like they would be with higher level programming languages such as Python and Java. No exceptions are thrown if any attempted access outside of the bounds of the buffer is made. So let's take a look at this vulnerable function here, at its source code as well as its disassembled code that's located within the text section. So the very first thing that happens, if you remember the diagram of a stack frame, is that we push the RBP onto the call stack as the saved base pointer, and then we update the base pointer register to hold the contents of the current stack pointer. And then we decrement the stack pointer because the stack section grows to lower addresses to make enough space in the stack for anything that we may need to execute the vulnerable function. Here we're loading our character string pointer onto our stack frame. And then here we're loading that pointer into our RDX as well as the location of our buffer into our accumulator register, which are then both loaded into our RDI and RSI function call registers. Right, and so we load these values into our function call registers because we want to prepare these registers in order to make the call to the string copy function, which is going to eventually execute our exploit by overriding the buffer and areas of the stack frame. So if we do some quick back of the napkin math, 0x20 is going to be 32 bytes of space made on the stack. 0x18 is going to be us writing our 8 bytes of the character input string for the pointer, since addresses are 8 bytes, onto the stack space at bytes 17 through 24 inclusive. And then we're going to be writing our 16 bytes of the buffer. So the buffer is 16 bytes, taking up stack space from 0 to 16 bytes from the save base pointer for our buffer. So how do we conduct a buffer overflow? Remember our stack? And here is, for a reminder, our back of the napkin math. If we know how much space is being allocated on the stack and where exactly our input is being written to, we can calculate how many bytes to write to get to the saved return address of the caller. So if we have 16 bytes needed in order to fill up our buffer, and 8 bytes needed to overwrite our saved base pointer, and another 8 bytes needed to overwrite the caller's return address, then we simply need 32 bytes in order to hijack the control flow of this program. So now let's get to the fun part. Let's send a payload that smashes the stack and overwrites all the way to where the return address is saved. And then we can override it with our address of the secret function located in the text section of our address base. So remember that the code section or the text section contains all of our instructions. And at any point, these locations can be accessed with our disassembler, since the code section stays the same regardless of where we are in our program's execution. So here we send this payload of 24 characters of A, which is 24 bytes. And then we have our last remaining 8 bytes with the address of our secret function within the code or text section of our address base. And here we've executed our exploit. Instead of jumping back to main, our function jumps to the address of secret stored within the text section of our address space and executes it instead. We've successfully exploited this vulnerability. And so now let's quickly go over shellcode injection. What is shellcode? You can say that shellcode is a small specialized machine code used as a payload in software vulnerability exploits, typically designed to spawn a command shell. And why a command shell? Command shells are the ultimate gateway to full attacker control over a victim process. And we've already stack smashed to exploit unprotected buffers to change the return address. Is it possible for us to do the same to execute our shellcode on the victim process as well? So can you spot the vulnerability this time? If you said the vulnerability was at line 6, then you would be correct. So given a large enough buffer, we can inject shellcode into the buffer and overwrite the return address to instead jump to our buffer instead of to the code in our code section like we did for our previous buffer overflow. So here we've overwritten everything in our buffer as well as our saved RBP. And instead of writing the address to somewhere within our code or text section, we've written the address of the start of our buffer where our instruction pointer can start executing our shellcode. And then now we'll jump to our shellcode and execute our shell, which will give us control over the victim's process. And if you're interested, this is a good paper called Smashing a Stack for Fun and Profit. Next, we'll be talking about data-only attacks, return to libc, buffer overread, and more.